Today we're going to extend our discussion of equilibrium as it pertains to two classes of compounds that we may be familiar with, acids and bases. Now, we may be familiar with some acid-base behavior. Acids tend to have a sour taste. They tend to have a stinging sensation to the touch. Bases tend to have a slippery feel to them, and they tend to taste sour. Now, I would not suggest that you go out and you taste something in order to determine whether it's an acid or a base. Many bases you're not likely going to find in the edible portions of your grocery store. At the same time, tasting anything to see whether it's acidic or basic is not the best way or any way to go about determining the nature of a substance. But our discussion here today is going to be based on the properties, a description of these compounds, and how the concept of equilibrium can dictate their behaviors in solution. Now, there are several theories that have been put forth that attempt to describe acids and bases, or what makes an acid and what makes a base a base. Dating back to the 1800s, we see a definition given to us by Swedish scientist Svante Arrhenius. Arrhenius proposed that an acid was a substance that, when placed in water, would increase the amount of hydrogen ions. Now, in doing so, we would see a substance that would dissociate or break apart, ionize in order to form H plus and a counter anion. In other words, H plus and whatever else was left minus. For example, hydrochloric acid would break apart into H plus and Cl minus. A base was a substance that, when dissolved in water, would increase the amount of hydroxide ions in solution. So sodium hydroxide, which would dissociate in order to give Na plus and OH minus, would be considered as a base. In the 1920s, a different path was taken in order to describe acids and bases by Danish scientist Johannes Bronsted and British scientist Thomas Lowry. They instead decided to focus on the idea of that hydrogen ion. A hydrogen ion, a positively charged hydrogen ion, is nothing more than a proton. So Bronsted-Lowry theory describes an acid as being a proton donor, or a substance that is willing to give up an H plus. Well, you can only give something that someone is willing to receive. So they described a base as being a proton acceptor, or a substance that was willing to take on that H plus. Now, Arrhenius's definitions are quite narrow in scope because it limits the discussion to simply aqueous solutions, things that are dissolved in water. While Bronsted-Lowry considers water as a possible medium, it's not limited to that. Now let's consider water as a proton acceptor, or in this instance behaving as a base. When an acid dissolves in water or dissociates, then it's going to produce H plus, or a proton. Now that proton is going to see all of the water molecules, and it's not going to exist in solution by itself for long. We're going to see that hydrogen interacts with water molecules in order to form the hydronium ion, H3O plus, a complex polyatomic ion. There are other clusters of hydrated protons that can be formed. On the right-hand side of this slide, you can see H5O2 plus and H9O4 plus, all the result of hydrogen bonding. But commonly, we equate H plus with H3O plus in aqueous solutions of acids. Now, in order to be considered a Bronsted-Lowry acid, a substance must have at least one ionizable or removable proton to donate. In order to be considered a Bronsted-Lowry base, you must have the ability to receive that proton. And in order to do so, you must have a non-bonding or a lone pair of electrons. If you look at the slide, you will see that water indeed has a lone pair of electrons on the oxygen that can receive that proton. H plus being nothing more than a proton sees a lone pair of electrons, and hydrogen would love to have two electrons around it. So it shares the two electrons in the lone pair, resulting in the formation of the hydronium cation. Now, with this being said, water is a very interesting substance. We saw on the previous slide that water can act as a Bronsted-Lowry base and accept a proton from an acid. But since water also has an ionizable hydrogen, it can donate a proton and act as an acid. Below we see the reaction of ammonia with water in order to form the ammonium cation and the hydroxide anion. Since water in this instance has donated a proton, it walks away looking like OH minus, while the ammonia takes on that proton because ammonia in the nitrogen has a lone pair of electrons that is willing to accept that proton. Ammonia walks away from this interaction looking like the ammonium cation. For this reason, since water can both donate a proton and accept a proton, water is considered to be amphiprotic. Now, whatever is left after an acid has donated its proton, that counter anion, we call a conjugate base. Similarly, once the base has taken on that proton, we see the formation of a conjugate acid. Now, are these things acids and bases? Well, sure they are, especially when you consider that these particular reactions are dictated by equilibrium, which means that the reaction can happen from left to right or from right to left. Since we're talking about a proton being transferred, one can imagine that in going from left to right, nitrous acid, as is listed below, will lose a proton and in doing so become NO2 minus or the nitrite anion. But if we look at the reaction in reverse, NO2 minus, the nitrite anion, can take on an H plus and become nitrous acid. So the nitrite ion serves as a base in the reaction as it proceeds from right to left. Here we see a comparison of the relative strengths of a series of acids as well as a series of bases. Now, the concept of acidic strength or basic strength lies solely in the extent of dissociation. A strong acid will completely dissociate in water, completely breaking apart into H plus and its counter anion. A weak acid will only partially dissociate into H plus and its counter anion. The stronger the acid, the weaker its conjugate base. Now, an acid and a conjugate base differ by H plus. The acid has the H plus, the conjugate base does not have the H plus. So a strong acid will produce a base that has negligible basicity. In other words, that reaction will not go in both directions. If it completely dissociates, equilibrium does not dictate the reaction. But in the case of a weak acid, where we see partial dissociation, then the conjugate base is also a weak base. As you go down this chart, from left to right, you can see an acid combined with its conjugate base, or rather paired up with its conjugate base. In every acid-base reaction, the position of equilibrium is going to favor the transfer of a proton from the stronger acid to the stronger base. In doing so, we're going to see the formation of the weaker acid and the weaker base. Take into consideration water and the hydronium ion as a conjugate acid-base pair. Water serves as a base, the conjugate base to the hydronium cation. Now, since water is a much stronger base than the chloride anion, water is more willing to take on that proton than chloride would be. So the equilibrium for this reaction is going to lie to the right. Since water is a much stronger base, the equilibrium is going to lie far, far to the right, suggesting that the K value, the equilibrium constant, the ratio of products to reactants, is going to be much, much larger than 1. It's so large that this reaction is essentially said to go to completion. Notice the single-sided arrow in this reaction mechanism. Acetic acid, on the other hand, CH3COOH, does not go to completion in its dissociation. When it reacts with water, we see the formation of the hydronium cation as well as the acetate anion. Now, since the acetate anion is a stronger base than water, the equilibrium for this system is going to lie to the left. In other words, favoring the formation of reactants as opposed to products. If we were to look at a reaction mixture for acetic acid in water, most of the acetic acid would remain intact as opposed to dissociating into the acetate anion. Now, I discussed previously the idea that water was amphiprotic, able to both donate a proton and accept a proton, acting as a Bronsted-Lowry acid and a Bronsted-Lowry base, respectively. Water is also considered to be amphoteric, a substance that can act as an acid or a base. Now, this definition, the idea of amphoteric, is not limited simply to the Bronsted-Lowry definition of what an acid is and what a base is. In pure water, some water molecules can indeed act as acids, while some can act as bases. If we see a water molecule acting as an acid, it is going to donate a proton to a water molecule that is acting as a base. In doing so, the water molecule on the left donates its proton and walks away as a hydroxide anion. The water molecule on the right walks away having accepted that proton, now looking like the hydronium cation. So the conjugate acid-base pairing is interesting. We see a water molecule as an acid having the hydroxide anion as its conjugate base. A water molecule as a base having the hydronium cation as its conjugate acid. Since this process happens in water by itself, this is known as the autoionization of water. It's also sometimes called the autoprotolysis of water, since water is protonating or donating a proton to another water molecule. This is a special case of ionization, one that speaks to a special value of K. If we evaluate the equilibrium constant for the reaction on the previous slide, we will see that the equilibrium expression becomes the concentration of our products over our reactants. Well, since our reactants are both pure liquids, we're simply looking at the concentration of our products multiplied by one another. This special equilibrium constant, since it's the product of the hydronium cation and the hydroxide anion, in a sample of water. It's referred as the ion product constant for water, or the ion product of water. K sub C has a special value, which we dub K sub W. At 25 degrees Celsius, it's important to note that the value of K sub W is equal to 1 times 10 to the negative 14th power. Now, pure water at 25 degrees Celsius is said to be neutral. That is, that there's just as much H plus in solution as there is OH minus. Aqueous solutions can also be considered neutral, but they can be acidic or they can be basic. If a solution is neutral, as is the case with pure water, then we see the hydronium ion concentration, or the amount of H plus, is equal to the hydroxide anion concentration. If a solution is considered acidic, that means it has more H plus, or more hydronium ion, than hydroxide anion. If a solution is considered to be basic, there's more hydroxide in that solution than there is hydronium, or H plus. At the bottom of the slide, we see three different solutions. One which is essentially pure water, in which we see the same amount of H plus and OH minus. An acidic solution of hydrochloric acid, which obviously has more H plus than OH minus. And a basic solution of sodium hydroxide, in which we see more hydroxide anion than H plus. But it should be noted that at 25 degrees Celsius, the hydroxide anion concentration times the hydronium cation concentration is going to equal 1 times 10 to the minus 14th, specifically for relatively dilute solutions of acids and bases in water. pH is a means of expressing the amount of hydrogen ion or hydronium ion in a given solution. pH is equal to the negative log of the hydronium ion concentration, or the negative log of H plus. The more hydronium ion in solution, the lesser the value for the pH. That's the way the logarithmic scale works with respect to a negative log. A neutral pH is going to be 7. An acidic pH is going to be lower than 7, and a basic pH is going to be greater than 7. On the right-hand side of this slide, we see a series of substances with respect to their pH values. We also see a measure known as pOH, which is a method of expressing the hydroxide anion concentration. At the top of the slide, we see things that have a greater pOH and a lesser pH. At the bottom of the slide, we see substances that have a greater pH but a lesser pOH. In each instance, you will notice that if you combine the pH with the pOH, then you will get 14. Now, the P in pH, or the P in pOH, speaks to a specific function known as a power function. Now, this power isn't the same as an exponent. It's a different power function that historically is spoken of. The power function tells us to take the negative log of a specific quantity. So the pOH would be the negative log of the hydroxide anion concentration. The negative pKw would be equal to the negative log of Kw. Well, because the hydroxide anion concentration times the hydronium ion concentration, that is Kw, is equal to 1 times 10 to the minus 14th. We can take the negative log of that expression, suggesting that the negative log of Kw, or pKw, is indeed 14. A little bit of mathematical legerdemain a little hand waving, a little sleight of hand suggests that the pOH of a solution plus the pH of that solution will indeed equal 14, as we saw on the previous slide. Now, there are a few ways that we can measure pH. One way is to use a device known as a pH meter. They tend to be relatively accurate. The electrodes in question indicate very small changes in voltage in order to detect pH. Another way to measure pH is with a series of compounds known as indicators. Indicators tend to give less accurate results, but the measurements can be done relatively quickly. An indicator, specifically an acid-base indicator, is a substance that appears to be one color in its acidic form or in acidic solution and one different in its basic form. Phenolphthalein, for example, is a common acid-base indicator. In acidic solutions, phenolphthalein appears to be colorless, but in basic solution it appears to be pink. Bromothymol blue is another example, appearing yellow in acidic solution and blue in basic solution. From our discussion in chapter 4, hopefully you will remember that there are 6 strong acids. The 6 strong acids are hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric acid. Their formulas being presented here. By definition, these are strong electrolytes, which means that they will completely dissociate in water. These reactions will go to completion, therefore are not dictated by equilibrium. So we see in a solution of strong acid that the concentration of the acid is essentially the concentration of H plus or H3O plus. If I had a 0.3 molar solution of hydrochloric acid, it would dissociate in order to form a 0.3 molar solution of hydronium cations and a 0.3 molar solution of chloride anions. Strong bases similarly dissociate to completion. Strong bases are generally the known soluble hydroxides, which include all of the alkali metal hydroxides, sodium, potassium, cesium, and the like, as well as the heavier alkaline earth metal hydroxides, things like calcium hydroxide, strontium hydroxide, and barium hydroxide. It should be noted that these heavier alkaline earth metal hydroxides have a fairly low solubility, but are still considered to be strong bases. These substances will completely dissociate when placed in aqueous solution. Now, for a weak acid dissociation, since it is an equilibrium situation, we can see the general equation listed above, where HA, representing an acid, dissociates by reacting with water in order to produce H3O plus, and A minus, that being the counter anion as a result of the dissociation. Since this is an equilibrium situation, then in fact there will be a K sub C value associated with it. Here, this is a special K sub C value that we call K sub A, or the acid dissociation constant. The larger the value of Ka in general, the stronger the acid. Well, let's think about that statement. The larger the Ka, the greater the ratio of products to reactants. That means that this reaction is going to dissociate or reflect the dissociation more, the reaction going from left to right, than the reaction going from right to left. The larger the value of K sub A, the more likely that products are going to dominate the reaction mixture at the end of the day. The lesser the value of K sub A, the weaker the acid. the lesser the value of K sub A, the more likely we are to see our acid remain intact as opposed to dissociating. Here we see a series of weak acids in water. Chlorous acid, not to be confused with chloric or perchloric or hypochlorous, has a K sub A value of 1 times 10 to the minus 2. Benzoic acid has a Ka value of 6.3 times 10 to the minus 5. Chlorous acid is a stronger acid than benzoic acid, but chlorous acid is by no means considered to be a strong acid. We can see this trend continuing through acetic acid, hypochlorous acid, all the way down to phenol, in which we see a Ka value of 1.3 times 10 to the minus 10th. Of all the acids listed on the previous slides, phenol represents the weakest acid of the bunch, since it has the lowest K sub A value. Once again, I can't hammer home the importance of understanding the difference between a strong acid and a weak acid. A strong acid is going to completely dissociate, while a weak acid is only going to partially dissociate. In a solution of weak acid, we're going to see a significant amount of acid remaining intact. Now it's time to use some of the knowledge that we've obtained in order to solve some problems. In the same way that we could calculate K sub C when given the equilibrium concentrations of all the reactants and products in a reaction mixture, we can do the same with an acidic mixture. Instead of solving for K sub C, we're going to be solving for the specific Ka. So here goes. The pH of a 0.1 molar solution of formic acid at 25 degrees Celsius is 2.38. Calculate the Ka value for formic acid at this temperature. Well, if we know the formula for formic acid to be HCOOH, then we can write the acid dissociation equation suggesting that formic acid reacting with water will give rise to the hydronium ion and the formate anion. Now, you may have never heard me say the words formate ion. You may have never encountered the term formate anion. But all you need to know is that an acid is going to lose an H plus in solution. So whatever is left over after you lose H plus is going to be your counter anion, or the HCOO minus. So now that we know how the acid dissociates, we can determine Ka if we know the equilibrium concentration of all three components that get included in the K sub A expression. Since we know the equation that speaks towards the dissociation of the acid, we know that for every 1 mole of hydronium cation formed, we also see 1 mole of formate anion formed. So the concentration of hydronium is going to be the same as the concentration of our formate. If the pH is equal to negative log of the hydronium ion concentration, then that mathematical function can be reversed to suggest that the hydronium ion concentration is equal to 10 raised to the negative pH. And that's the way the logarithmic function works. So 10 to the negative 2.38 is going to give us the concentration of hydronium ion, and it turns out to be 4.2 times 10 to the minus third power. Well, now that we know the equilibrium concentration for our products, we can set up an ice table to figure out the equilibrium concentration for our reactants. As always, with an ice table, we need to understand what we know and what we're looking for. We know the initial concentration of formic acid to be 0.10 molar, and we know that those ion concentrations are 0. So we can find the equilibrium concentration of formate, or rather formic acid, since we know the equilibrium concentrations of our two ions. Solving for the concentration of formic acid at equilibrium gives us essentially the same as the initial concentration. If we're monitoring this to two significant figures, then 0.10 molar formic acid dissociates in order to form a 0.10 molar solution of formic acid. Since we now have our three equilibrium concentrations, we put it into the expression for case of A, and we find that the acid dissociation constant for formic acid is 1.8 times 10 to the minus fourth power. Now we see that our initial concentration for formic acid was essentially the same as our final concentration. With this being said, we have to wonder how much of our acid truly ionized. In order to figure out the percent ionization, we take the amount of hydronium ion that was formed divided by the concentration of our acid initially and multiply that by 100 in order to make a percent. For this particular example, we found that our equilibrium concentration of hydronium was 4.2 times 10 to the minus 3. We know that our formic acid concentration was 0.10 molar. Doing this calculation shows that 4.2% of the formic acid actually dissociated in order to form our hydronium ion. We can also do the reverse. We can use the Ka value in order to calculate the pH of a solution of acid dictated by equilibrium. This is going to be essentially the same process by which we describe all other equilibrium reactions. We're going to write down the chemical equation. We're going to write down the expression for the equilibrium constant, and then we're going to set up that ICE table. We understand that we don't know how much substance is going to dissociate, how much of our acid is going to react with water in order to produce those ions. So whenever we have an unknown, we're going to express that as a function of change. Typically, algebraically, we would use the value of x. Finally, we're going to substitute those equilibrium concentrations into the equilibrium constant expression and solve for x. The only difference in these problems, in your typical equilibrium problems, is that we can make an assumption or two somewhere along the way. This assumption may prevent us from having to do things like the quadratic equation, but we'll see. Here's an example. Here we want to calculate the pH of a solution of acetic acid of molarity 0.30 molar. So we write down the equation. We see the resulting formation of the acetate anion and the hydronium cation. Writing out the equilibrium constant expression that we call the acid dissociation constant gives us the concentration of hydronium times the concentration of acetate divided by the concentration of acetic acid. Products over reactants stoichiometrically weighed as exponents. Finally, we set up this ICE table, which suggests that the equilibrium concentration of our three substances are all reflected by that change that we call X. But here's where things get a little different for us. When we set up the equilibrium constant expression, when we input those equilibrium concentrations into the expression, we can now make an assumption. If we assume that the amount of acid that dissociates is very, very small, in the last instance we saw 4.2%, then we can essentially say that the initial concentration of acid is the same as the final concentration of acid. Not a whole lot dissociates. So we can make our problem a lot easier if we assume that there's not a lot of dissociation taking place. And with weak acids, we know that weak acids do not dissociate completely. They only dissociate partially. So for now, that is a reasonable assumption to make. In doing so, the denominator of our equilibrium constant expression condenses down to essentially the initial concentration. Now we're simply solving for x squared, which we can then solve for x, and we don't have to use that pesky quadratic equation in order to solve for it. Now, previously I mentioned that we could measure the pH of a solution by using a pH meter, a device that takes into consideration the electrical conductivity produced in a solution. Well, this is because there's a difference in conductivity based on the number of ions in solution. Now, for the most part, the acids that we've dealt with so far have been able to donate one proton. Those acids we would classify as being monoprotic, since they are willing to donate only one proton. But there are a series of acids that are able to donate more than one proton. These acids would be characterized as polyprotic acids. In the case of a polyprotic acid, it should be noted that it's always easier to remove the first proton from a polyprotic acid than any additional proton. Some polyprotic acids can donate 2 protons, some can donate 3 protons. Now, when determining the pH of a solution of a polyprotic acid, we should consider only the first dissociation if the difference between the first and the second dissociation is greater than 3 in terms of the Ka values. Here we see a series of polyprotic acids, alphabetically from ascorbic acid, also known as vitamin C, all the way down to tartaric acid. In each instance, we see a different K sub A value, and since there are multiple K sub A's, we would dub them as K sub A1, K sub A2, K sub A3, and so forth. Now, Ka1 for sulfuric acid, it should be noted, is very large. Now, why is sulfuric acid even on this list? If you'll remember, sulfuric acid is a strong acid. So its reaction should not be considered an equilibrium situation. But that's only in its first dissociation. When removing the first proton from an atom, or rather a molecule of sulfuric acid, that goes to completion. But the second dissociation, removing an electron, or rather a proton, from HSO4 minus, is going to require an equilibrium discussion. If you'll take a look at phosphoric acid, you will see that the differences in the Ka values vary on the order of about 5 orders of magnitude between the first Ka, the second Ka, and the third Ka. 7.5 times 10 to the minus 3, 6.2 times 10 to the minus 8, 4.2 times 10 to the minus 13. 5 orders of magnitude separating each of them. With that being said, if we were looking at the pH of a solution of phosphoric acid, that pH would be dependent primarily on the K sub A value for the first dissociation. Now, we spent the majority of our time talking about acids in equilibrium. Now we're going to turn our focus towards bases. We mentioned that ammonia was a weak base and continues to be a weak base. Like weak acids, weak bases also have equilibrium surrounding their dissociations. So the K sub C value, we would dub a K sub B, which is the base dissociation constant. Now, the equilibrium calculations work exactly the same for acids as they do for bases. Rather than using the case of A value, we would instead use the case of B value. It should also be noted that many bases contain nitrogen because nitrogen tends to have that lone pair of electrons on it willing to accept willing to accept a proton. Now, in general, we can categorize weak bases in one of two ways. They tend to be either neutral substances that have an atom that has a non-bonding pair of electrons that can accept that proton, just like ammonia, or they're the ions, specifically the anions of weak acids, the result of a weak acid dissociation, producing a conjugate base. Here we see some weak base dissociation constants. Ammonia having a dissociation constant of 1.8 times 10 to the minus 5. Hydroxylamine having a case of B value of 1.1 times 10 to the minus 8. Furthering this discussion, we continue to see atoms that have a lone pair on them able to accept a proton. The carbonate anion we see has a case of B value of 1.8 times 10 to the minus 4. The hypochlorite ion, 3.3 times 10 to the minus 7. So here we have another problem. How do we determine the pH of a basic solution, specifically the solution of a weak base? What is the pH of a solution that is 0.15 molar ammonia? Well, the equation is going to suggest the formation of the ammonium cation and the hydroxide anion. Now, in order to determine the pH, we're going to need to know the concentration of the hydronium cation, and that does not appear to be anywhere in this expression. Well, don't worry. In just a moment, we're going to be able to use that hydroxide ion concentration in order to determine our hydronium ion concentration. So we're going to continue to do this as any other equilibrium problem. We're going to set up the equilibrium constant expression. We know the value of K sub B, so then we set up our ice table. Knowing what we know initially, knowing what we know about equilibrium, which isn't a lot, we have our unknowns set up to suggest the equilibrium concentrations, all with respect to the change that takes place. We know that ammonia does not completely dissociate. We know that it's not going to cause the total ionization resulting in OH minus. So equilibrium is suggested, and we're going to use our ice table in order to determine the information that we need. Once again, when we input those values into the equilibrium constant expression, we can solve for our unknown. Now, once again, since this is a weak base, we can make the assumption that not a lot of it is going to dissociate. So we can say that our initial concentration of base is the same as our final concentration of base. If this is the case, then when we solve for X, which is the change in concentration of our hydroxide ion, we find X to be 1.6 times 10 to the minus 3. So that's the concentration of our hydroxide. We can solve for the concentration of our hydronium ion concentration, or we can go straight to the source and find our pH. Since we know the relationship between pH and pOH, when you add pH and pOH together, you get 14. If we find the pOH to be the negative log of the OH concentration, or the hydroxide ion concentration, for this solution we find the pOH to be 2.8. And then when we subtract that from 14, we end up with a pH of 11.2. Now we're going to explore the relationship between the acid dissociation constant of a given acid and the base dissociation constant of its conjugate base. You will notice that for a strong acid like nitric acid, that its conjugate base, in this instance the nitrate anion, has negligible basicity. So the equilibrium constant for these processes are essentially going to be really, really large and really, really small, respectively, to the point where equilibrium does not describe their dissociations. But for something like hydrofluoric acid, a weak acid with a Ka value of 6.8 times 10 to the minus 4, the fluoride anion, or its conjugate base, has a K sub B value of 1.5 times 10 to the minus 11th. If we look at the subsequent series of acids and conjugate bases as they are paired up, you will see that as the Ka value decreases, that the Kb value increases. That's a very interesting relationship to take note of. What mathematically is the relationship between K sub A and K sub B for a conjugate acid-base pair? Well, here is the mathematical relationship between the Ka value and the Kb value for a conjugate acid-base pair. Multiplying K sub A for an acid times K sub B of its conjugate base is going to give us K sub W. And if you remember, at 25 degrees Celsius, K sub W is equal to 1 times 10 to the negative 14th. So if you know one of the two, then you can determine the other by a simple calculation. Now, we've spent the entirety of our time talking about the properties of acids and bases themselves. But there are some substances that would seemingly neither be acidic nor basic based on our previous definitions, which would give rise to acidic properties or basic properties. Many ions in solution will react with water in order to produce or create H plus or OH minus. The reaction with water is often known as hydrolysis. So in order to determine whether a salt is an acid or a base, you need to look at what happens once that reaction takes place, once the dissociation of a salt in water occurs. You have to look at the cation and you have to look at the anion, but you have to look at them separately. The cation can be either acidic or neutral. The anion can be acidic, neutral, or it could be basic. In short, anions produced by strong acids are neutral. For example, hydrochloric acid dissociates to form H plus and Cl minus. Cl minus will not react with water, so OH minus can't be formed. It is a neutral component. Anions of weak acids tend to be conjugate bases, so they can create OH minus in water. For example, if we look at the acetate anion reacting with water, it's going to give rise to the formation of acetic acid and the hydroxide anion. So it will produce OH minus in water. Protonated anions from polyprotic acids can be either acidic or basic. You have to look at the relationship between the acid dissociation constant and the basic dissociation constant for the ion itself. If K sub A is greater than K sub B, then the anion will be acidic. If K sub B is greater than K sub A, then the anion will be basic. As far as cations are concerned, the group 1 metals and the group 2 metal cations are neutral. Those alkali metal cations, things like potassium, cesium, lithium, and those alkaline earth metal cations, things like calcium, barium, magnesium. Those tend to be neutral. Polyatomic cations tend to be the conjugate acids of a weak base. We take into consideration the ammonium cation. Well, the ammonium cation is the conjugate acid for ammonia. It has taken on the H plus from ammonia. Transition metals, their cations tend to be acidic. So the iron cation tends to be acidic when placed in solution. Well, how can this be? Why is this true? These substances do not have any hydrogens in order to donate. So how is it that these substances, these transition metal cations, can be acidic? For transition metals and post-transition metals, their ions in solution tend to attract water molecules, specifically the unshared electron pairs on the oxygen in water molecules. In doing so, they become hydrated. The larger the charge on the metal cation, the stronger the interaction between the ion and the oxygen on the hydrating water molecules. So since there's a stronger attraction there, this essentially weakens the OH bonds in the water molecules. Now this is going to allow the hydrogen to more easily dissociate or break apart, and this facilitates proton transfer from those water molecules to other solvent water molecules. So this will allow an H plus to come from a hydrated cation water molecule to one that is simply a water molecule in solution. With this being said, that gives us the definition of an acid. And these are some examples of hydrated metal cations in aqueous solution and a peek at their acidic properties. If we look at their acid dissociation constants, or the case of A value for these ions, we should note that once again, the greater the positive charge, the stronger the interaction between these ions and the hydrated water molecules. So that's going to result in a higher case of A value. Fe plus 3, or the ferric cation, has a case of A value of 6.3 times 10 to the minus 3, while the nickel plus 2 cation doesn't experience that strong of an attraction. That results in a case of A value that is much less, or 2.5 times 10 to the minus 11. So salt solutions can be acidic, basic, or neutral. In order to determine, we have to look at the combination of the ions in solution. Salts that are derived from a strong acid and a strong base are neutral. Salts that are derived from a strong base and a weak acid are basic. Salts that are derived from a weak base and a strong acid are acidic. Salts that are derived from a weak acid and a weak base can either be acidic or basic. This is where the equilibrium rules begin to apply. We need to compare the case of A value and the case of B value for the hydrolysis of each of the ions. In the case of the ammonium cyanide ion, both of the ions undergo significant hydrolysis, forming NH4 plus and Cn minus. The question is the salt solution acidic or is it basic? Well, it turns out the Ka value for the ammonium cation is smaller than the Kb value of the cyanide anion, so the solution should in fact be basic. There are a series of factors that govern or affect the strength of an acid. Such factors include the bond polarity, the bond strength, and the conjugate base stability. In the case of bond polarity, let's assume that we have an acid of form HA, where H represents the hydrogen and the A represents essentially the counter anion that is to be formed, or the conjugate base. As the bond polarity increases, in other words, with more polar OH bonds, we see more electron density being pulled away from the hydrogen, making it easier to leave in the form of H+. So with an increase in bond polarity, we're going to see an increase in the strength of an acid. As far as bond strength is concerned, as the bond strength decreases, then the acid strength tends to increase. Once again, if breaking that OH bond is easier, then that's going to make it easier for the hydrogen to come off into solution. And lastly, the stability of the conjugate base. In short, the greater the stability of the conjugate base, the stronger the acid. Binary acids are acids that are made up of two elements. Obviously, one of them has to be hydrogen and another element. So when comparing acid strengths in binary acids, the HA bond strength is typically the most important factor. In a given period, for example, looking at the halogens, we see that bond polarity is the most important factor to determine acid strength. HF being a weak acid, HCl being a strong acid, HBr being a strong acid, HI being a strong acid still. So with this general idea in place, we would consider hydroiodic acid to be the strongest of the hydrogen halide acids. Oxyacids, or also known as oxoacids, are ternary compounds made up of three elements, where one is hydrogen, a second one is oxygen, and a third is a nonmetal. Now, in oxoacids or oxyacids, the ionizable hydrogen is connected to the oxygen. And in general, as the electronegativity of the nonmetal element increases, so does the acidity for acids that have the same structure. Now, if we have an element that can form multiple oxyacids, then the oxyacid with more oxygen atoms tends to be more acidic. We can compare sulfuric acid with sulfurous acid, H2SO4 with H2SO3. Since sulfuric acid has more oxygens, it tends to be more acidic. At the bottom of the slide, we see hypochlorous acid as opposed to chlorous acid. Molecules with the formula HClO and HClO2 respectively. The more oxygens, the stronger the acid, as is reflected in the Ka values. Now we could continue in this sequence because there are two other oxyacids that typically form involving chlorine. We also have chloric acid, HClO2, which would be a stronger acid than chlorous. And then we have perchloric acid, HClO4. And we know perchloric acid to be one of the 6 strong acids, so obviously it has a strength that is greater than chloric, which has a strength that is greater than chlorous, which has a strength that is greater than hypochlorous. Another way of expressing this idea is that as the oxidation number of the element increases, so does the acidity. Another class of acids is carboxylic acids. These are organic acids that contain the COOH group or the carboxyl group. Acetic acid is an example of a carboxylic acid having the formula CH3COOH. Now, factors that contribute to the acidic behavior of carboxylic acids include the other oxygen that is attached to the carbon. That oxygen tends to draw electron density away from the OH bond, which increases the polarity of that bond. Also, the conjugate base or the carboxylate anion tends to have resonance forms that stabilize the ion itself. Finally, we have one more description of acid-base behavior. Svante Arrhenius gave us the idea that acids would dissociate in order to form H plus, and that bases would dissociate to give us OH minus. The Bronsted-Lowry theory suggested that acids were proton donors, while bases were proton acceptors. But the idea of a Lewis acid and a Lewis base, named after American physicist Gilbert Lewis, tells us that Lewis acids are electron pair acceptors, while Lewis bases are electron pair donors. Now, all Bronsted-Lowry acids are Lewis acids. All Bronsted-Lowry bases are Lewis bases, because each of those has to be able to donate a proton, and in doing so, it would donate a proton to where there is an electron pair. If it receives a proton, it is because it has an electron pair. So the Bronsted-Lowry definition also falls under the heading of Lewis acids and bases as well, but there are certain compounds that meet the Lewis definition that don't meet the Bronsted-Lowry definition. Let's take a look at ammonia. Now we know ammonia to be a base. Ammonia has the ability to accept a proton in the form of H plus in order to form the ammonium cation. So based on the Bronsted-Lowry definition, ammonia is a base. But if we look at it from the Lewis point of view, since it has that electron pair, it is able to donate that electron pair, donate that electron density towards forming a bond. And it forms a bond with the H plus in the form of the ammonium cation. But at the bottom of this slide, we can see it interacting with boron trifluoride, a substance that we know to be an exception to the octet rule, in that there are only 6 valence electrons around our central atom. Well, this Lewis base in the form of ammonia can donate that electron pair in order to form a bond between the nitrogen in ammonia and the boron in boron trifluoride. Well, we can use the concept of Lewis acids and Lewis bases to describe the acidic behavior of hydrated metal cations. You remember those transition metal and post-transition metal cations that we spoke of just recently? Well, it turns out that when those ions are in solution, they attract water molecules. Since the ions are positively charged, they attract the lone pairs on the oxygen in water. When a series of water molecules surrounds an ion, that process is known as hydration. Well, those hydrated metal ions act as acids by drawing electron density towards themselves and essentially away from the ionizable hydrogen in water, thus making it easier for those hydrogens to dissociate. Proton transfer becomes easier, therefore we see a stronger acid. The higher the charge, the stronger the metal-water interaction. And in general, the smaller the metal cation, the more acidic the ion. Well, that, ladies and gentlemen, wraps up our discussion of acid-base equilibria. Hopefully, you've learned a little something. Maybe you've learned a lot of something. Take care, stay safe, and have a great day.